morning. We will continue our lecture regarding power diodes, the PiN diodes. The previous lecture explained the difference between a conventional low power diode and a power diode. We saw the presence of this wide intrinsic layer. It is also important to note that this is a vertical structure. The anode of the device is on the top surface of the silicon. The bottom is on the bottom face. The cathode is on the bottom face. In this way, you can fully exploit the silicon surface, and you can have very high devices with a very large area and hence able to carry a large current. After also explaining how to design the intrinsic layer in order to sustain a given target voltage in reverse, that is the breakdown voltage, but this has been done with the one-dimensional model, we now refer to the real, more realistic structure of a PiN diode. First of all, this N+ region, the substrate where the cathode is manufactured, is not in scale, it's much thicker, can be some hundreds of microns. And the top surface, the anode, is not diffused or implanted on the entire area of the chip, because the side connection would be will have too many defects and would limit the breakdown voltage. The reality is that we use some very simple lithography technique in order to implant or diffuse the anode on the top surface. However, the presence of this window into the silicon dioxide layer means that the diffused region or implanted region here has this curved junction here. This is a two-dimensional view of the real structure. But if we think of this structure in 3 dimensions, we see that this window is not a linear window, but it is a rectangular or square window. And in the corners, the diffusion of the dopant is 3-dimensional and will have a spherical curvature. This is a problem for the breakdown. As you remember from the basic physics courses, a carved junction, a carved amount of fixed charge will increase the electric field in that point. And we know that if the electric field approximately reaches the critical value in some point of the device, we have the breakdown, and that is our limit. This slide has been added, I will give it to you later, just to report some nomenclature. One big problem of these technical courses is that many times we use new words whose meaning maybe is easy, sometimes is not. And I wanted to add this slide to tell you that the low doped region is named with different names in different contexts or in different slides. Sometimes I say intrinsic region, sometimes I say the drift region, sometimes I say the AP layer or the AP. Or sometimes you can also hear bulk region. It's always the same region, it's always the low doped intrinsic layer that is built in order to sustain the reverse voltage. However, when we say intrinsic, the accent is on the fact that it is not doped. When we say low, when we say drift, we want to stress the fact that in that region the layers just drift from one junction to the other, from one region to the other, without actually having much electrical behavior than the drift, just the drift or diffusion. Here the carriers just flow from the anode to cathode and vice versa. On the other hand, when we say epi layer or bulk, we are referring to the manufacturing technique. You should have studied, or you remember, that there are mainly two techniques to build, to have this low doped wide region. The first one is the epitaxy. That is actually the deposition of a crystalline layer over another crystalline layer. And when this is an epilayer region, we start from the substrate, and with an epitaxy process, we grow this intrinsic layer. This is done for low voltage devices, few hundred volts. For very high voltage devices, this layer is too thick in order to allow this epitaxy, that is also an expensive process. And in this case, maybe you use a bulk region. You start from a piezo semiconductor, a chip that is very lightly doped, the bulk. It is very wide, more than 150 microns. And then you diffuse the anode on the top and the cathode on the bottom. So the cathode is diffused in this case, it's not the substrate. But these are different names, but the object is always the same. This low doped region. Let us return to our two-dimensional and three-dimensional effects. As previously said, the presence of this window and the diffusion of the dopants here causes a two-dimensional curvature here. But if we imagine this window in 3 dimensions, we clearly see that the diffusion is divided into 3 regions. In the middle, we have a flat, one-dimensional plane junction. In the 4 sides, we have the 2-dimensional structure with the cylindrical junction. And in the 4 corners, we have curvature. Now, which is the analysis? Which is the effect of this junction? Can we obtain some analytical results to calculate the breakdown in these cases? Let us imagine that this is the diffused region. Let us imagine that we are, in the case of a cylindrical junction, we neglect the spherical junction at the corners. We imagine that the diffusion is isotropic, that is, this thickness is equal to the radio of the curved junction here. This is not exact. There is a difference in the ratio, in the radius there and in the thickness, but it is a reasonable assumption here. And we also assume that this thickness, this width here is much larger than this diffusion, and this is always the case. We can then analyze just this cylindrical junction here. When we are in this cylindrical case, it's better to move from the rectangular coordinates to the radial coordinates. And since there is no dependence on the electric field on the angle, we can say that here the electric field is just a function of the radius, the distance from the center to the edge of the depleted region. In this plot, the dashed line is the edge of the depleted region. The red region is the anode that is highly doped. We can always use the Gauss equation to calculate the electric field in the cylindrical region. The only difference is that the Gauss equation must be written in cylindrical coordinates. It can be done, it's not exactly easy, the equation that we obtain is this one. It is a simplified equation, since we assume that the electric field does not depend on the angle. It means that the derivative over theta are always 0. This is the equation. This is the charge concentration, that is Q multiplied by the doping. Obviously, we are in the lightly doped region. In the epilayer region, the doping is constant. It's not a function of R. We can integrate this first term between a generic abscissa R and RD, that is the edge of the depleted region. And we know that here the electric field is 0, because outside the depleted region we are in the neutral region with no electric field, and the electric field is constant, does not have steps, because we don't have layers of charge with very high concentration. The integration is not difficult. In the end, you get this relation for the electric field as a function of R. That is minus proportional to the doping divided by the epsilon proportional to Q. These are physical constants. These are not important. This is the depletion, the depletion width, and this is the point along the depletion width. As we do expect, this electric field is 0 if R is equal to RD. It means that here the electric field is 0. It was one of the conditions, the boundary conditions. And the electric field increases when we move from here towards the junction. We do expect that the electric field is maximum at the junction. When we substitute Rj, that is the radius of the junction here, we obtain in absolute value the maximum value of the electric field. That is a function of Rd square minus Rj square divided Rj. A simplifying assumption is that if the doping concentration is quite low, the depleted region is wide, Rd is much larger than Rj. And we can approximate the previous equation, neglecting Rj here with respect to Rd, and we get this equation, this relation for the maximum electric field for the cylindrical junction. Okay, this is a number. It is a function of the sign quantities. Now we can calculate the electric field, the maximum electric field, for a plane junction that has a width of the depletion region that is exactly equal to Rd minus Rj. This means that the radius here is constant, and when we move in the plane region here, this thickness is exactly equal to this radius, a reasonable assumption. We obtain, using the previous equation, the equations that we know, that the maximum electric field for the plane junction is Q and D multiplied Rd divided epsilon, and always neglecting Rj with respect to Rd. Now we can simply calculate the ratio between the maximum electric field for the cylindrical junction divided by the maximum electric field for the plane junction. This cylindrical should have been written with Y, not with I. Cylindrical is with Y. You see? Okay. These slides are full of errors as you see. This ratio, however, is simply, it is very simple because the physical constants are removed and also the doping, and we see that it is equal to Rd divided twice Rj. And this is much larger than 1, since RD is much larger than RG. Which is the point? The point is that, as we do expect, the electric field at the edge of the junction in the cylindrical region is larger than the plane junction. And the breakdown will happen there, earlier than when we expect. A similar analysis can be conducted for the spherical junction. Here we need to use the Gauss equation in spherical coordinates. We always assume that the electric field is only a function of r and not a function of the two angles theta and phi. The Gauss equation is this one and is slightly different. We can again integrate to get the electric field with the above highlighted boundary conditions. The electric field is 0 at the edge of the depletion region. Yes, it's integrating as a function of r. You get the electric field as a function of r. The maximum also is obtained for r equal rj. Again, you can neglect rj with respect to rd, and you get this final relation. This is the maximum electric field for the spherical junction. Again, you can calculate the ratio between the maximum electric field in the spherical junction divided in the cylindrical junction, and again you find that this is a number that is much larger than 1. Again, this is the critical point. If we have a structure like this, the breakdown would not happen on the plane junction, not on the cylindrical junction, will happen in the four corners, and will happen much before than what we expect, reducing our voltage capability. It's not a nice thing, because we lose a lot of our voltage capability. In this slide, we exactly plot the ratio between the actual breakdown voltage and the expected breakdown voltage for a plane junction. The red curve will show the value if we only had cylindrical junctions, and the blue curve represents the value that we actually have when we have spherical junctions. This is lower. In this case, we will say that we will have a premature breakdown. And how much premature? The value depends on the ratio between Rj, the radius of the diffused junctions, and the thickness of the depleted region at breakdown. If the junction is very shallow, with Rj very small, this value is dramatically low. It's 0.1. This means 10%. I'm designing for 600 volt device. I get 60 volt breakdown. If this value is more reasonable, okay, this value increases. But please note that the maximum value is below 0.7. It's below 70%. You can get from a 1 kV device, you get 600 volt device, 600 volt breakdown. Something must be done in order to prevent this premature breakdown. The typical design activity is isolating the most important cause of performance reduction and try to solve that. Trying to solve this one. When you solve this problem, you try to solve the next one. And here the first problem that we have are the spherical junction that are worsening the breakdown with respect to the cylindrical junction. However, this is a very simple problem
to be solved. This problem can be easily alleviated designing the curvature radius in the YZ plane on the chip surface much larger than Rj of the cylindrical region. The idea is, my problem is the mask that is square, because I have corners here. Just make a rounded corner. Okay, but how much rounded? The important point is that the radius of this corner must be much larger than the thickness of the junction. You end with a mask on the chip surface with these rounded corners. What are you losing? You are losing this chip area. This portion of your chip could carry some current that is, and on the other hand, this becomes inactive. So you are losing some current capability. But this is very small. For example, for the thickness of the junction, that is Xj or Rj, that is 10 micron, that is a reasonable value. 10 microns of junction is also quite big. The depletion region is 50 micron, and this is a reasonable value for 600 to 1 kV breakdown voltage device. If you use first J equal to 200 microns, if this area is if this side is 1 millimeter, hence this diode is 1 millimeter square of chip area, what you lose is less than 2% of the total area. Absolutely reasonable loss. The first point is then solved. Just make rounded corners. For very small chip in some low power or integrated application, you can also see round power devices. A diode that is just a circular layout. It is the extreme case of rounded edges, rounded corners. And this solves the first problem. But now, what about the cylindrical junction? It seems that we can't do anything about that. However, there are design techniques that are able to alleviate or almost solve the problem. To overcome the decrease of the breakdown voltage due to the lateral junction curvature, the two most widely used techniques, this is valid for the power diode, but also for other power devices. We said more than once that other power devices have a similar structure for the intrinsic layer. That is, there is always a junction and a thick low-doped layer that sustains the reverse voltage. And also for other power devices, we have the floating field rings and the field plates. Let's see how they work. We firstly concentrate on floating field rings. The design in this case is conducted creating some P plus diffused rings around the P plus anode region. This is indicated here in this picture. This is the anode. Okay? This metal is the anode contact. So this region is contacted. Then we have the silicon dioxide as a passivation layer, and is also a masking layer. And farther away, we have another diffusion, P plus diffusion. You don't need another mask. You don't need another diffusion implant. You just use the same mask and the same diffusion. The only difference is that here you don't have the metal plate that contacts this region to the anode. So this one is not the anode. This is a ring that is not contacted to anything, hence it is floating. The voltage of this region is not linked with some metal contact to some point. If we assume that the potential line in the y direction is the horizontal direction, are not altered by the presence of the ring, when the ring is not yet biased, this ring will be actually biased by the potential value as soon as the depletion region touches the ring and overcomes it. The idea is this one. When we are in reverse bias, this anode is at, for example, 0 voltage. Then you increase the cathode voltage, biasing the diode in reverse condition. A depletion region deploys along this junction and starts to extend here. Later it will go here. At this point, this ring is at 0 voltage because it is surrounded by the intrinsic layer that is neutral, and it is at 0 voltage. At a certain point, the depletion region will touch the P plus region. At this point, this P plus region that is highly conductive is biased exactly with the voltage that is now the voltage of this depletion region here. From this moment on, the depletion region will extend and will start having this kind of shape. The idea is, if you design this ring at the right distance from the main junction, with the right width, you can deploy this depletion region with smaller curvature. Without the ring, you have this depletion region that ends here, for example. With the ring, the depletion region ends here, and you have larger curvature. You tend to have a one-dimensional behavior. In this case, one single ring is shown. In reality, more than one ring is used. 3, 4, 5, 7. Each ring will reduce the curvature a bit, and in the end you get a depletion region that slowly goes to 0 in this direction. Some analytical relation can be used to quantitatively understand the behavior of the floating ring. We can use the Poisson equation for the plane case in the y direction, the equation 14, starting from the lateral boundary of the P plus anode from here. And we can integrate using the boundary conditions that V equal to minus VR here. We assume that we are reverse biasing the anode, and V is equal to 0 at the end of the depleted region. The Poisson equation is this one. In the one-dimensional version of the Poisson equation is this one. The second derivative along y of the voltage is equal to minus the derivative of the electric field with respect to y. That is equal to minus q and d divided epsilon. You can integrate twice with the given boundary conditions, and you get, obviously, you get a parabolic equation, you are integrating twice a constant value, you are obtaining a parabolic equation for the potential along this y region, a y direction. When VR, the reverse bias, is increased, the depletion region WD extends in the y direction and reaches the floating ring at W equal WS. If the ring is properly placed, this depletion region will be smaller than the thickness of the depletion region at breakdown. Otherwise, we get the breakdown before reaching the floating ring, and the floating ring is unuseful. At this point, the voltage bias of the field ring at y equal WS will be this value, the voltage of the floating ring, substituting WS as instead of y. There are two limit cases. We can understand what happens in the two limit conditions. First of all, the distance of the floating ring is very, very small. Vs, that is this distance here, the distance of the floating ring from the main junction, is almost zero, it's very small. In this case, 0, 0, the field rate voltage is minus VR. Nothing is changed. The floating ring has the same voltage as the main ring, as they were in contact. Clearly, you get the exactly same breakdown voltage as in the presence of the cylindrical junction, because the curvature here is exactly the same as for the main junction without the floating ring. Second case, the thickness of the distance of the floating ring is large, tends to be equal to the thickness of the depletion region at breakdown. WS is equal to WB. In this case, the floating ring voltage is 0. It's not biased at all. Again, this means that there is no depletion region here, and the only depletion region is around the main junction. Also in this case, you don't get any advantage from the presence of the floating ring. You need to study the exact and optimal placement. This is done, can be done with these analytical results, or more realistically, with a number of numerical simulations. And in this case, it is shown that the best choice is a distance of the floating ring that is 1/3 of the thickness at breakdown, of the depletion region at breakdown, W3. As we can see here, for a particular case that is Rj divided WB equal 0.4, in this particular case, the ratio of the actual breakdown voltage divided the ideal breakdown voltage increases from 0.55 to, let's say, 0.7. If this were a 1 kV device, we are improving from 550 volts of breakdown to 700. It is good, but it is not enough. We want to reach 90% or 95% of the ideal voltage, and this can be done using more than one floating ring. This is also dependent on the ratio of the Rj of the junction, because this ring is usually made with the same diffusion process of the main junction in order to save money, to reduce the manufacturing cost. In order to get the ideal or almost ideal case, you use more than one ring. As you can see here, in this case, we have two rings. They are properly placed, and as you can see, instead of having this depletion region that ends here with the large curvature, the first floating ring extends the depletion, the second one extends it even more, and the final behavior with no large curvature points in the depletion region, and the actual breakdown voltage can be as high as 90 or 95%, the ideal one. This is the floating ring technique. Another technique is the field plate. The effect is more or less the same. The idea is using a metal plate over the silicon dioxide that is here. The presence of this metal plate here as a function of the voltage will change the doping, the current concentration here, not doping, the current concentration here. As an example, if this voltage is negative and this field plate is biased at higher voltage, higher than 0, this will attract negative charge here. The net effect is that the charge concentration here is larger than ND, than the doping concentration. Larger doping means higher electric field, and this means that the depletion region here is smaller, and the breakdown will happen even before than without the field plate. This is not a good choice. You see, the curvature, instead of finishing here, as it should be, curves even more, and we have a high curvature here. If the metal plate is negatively biased, case B here, we are actually repelling the negative charge, attracting positive charge. And the net effect here is as if we had a doping that is lower. With lower doping, the depletion region extends more, and we have this nice effect here. The curvature is smaller, and this will improve the breakdown voltage. We will have a breakdown voltage that is closer to the ideal value for the plane junction. It can also be noted that these positive charges here are more or less equal to the positive charge in this depletion region here. It's more or less the same. The physical effect is the same. However, the case A and case B are not practical. These need a third contact, anode, cathode, and field plate bias with a regulated voltage for it, and this is very expensive and impossible in real application. What is actually done is the case C. The anode contact is extended over the silicon, creating the field plate. The field plate has the same bias of the VR of the junction, but the important point is that a part of the voltage will drop on the silicon dioxide, and the actual voltage that will be seen here is smaller. We need to evaluate the equivalent voltage induced on the silicon surface as a function due to the presence of the field plate. We can't do this in a full analytical way. We need to simplify a number of aspects. The critical parameter for the evaluation of the voltage bias at the silicon surface is the oxide thickness of the field plate. We can evaluate the field, the electric field across the oxide using the Gauss law. This is the metal. This is a dielectric region, isolating region, that is the silicon dioxide. The thickness is the thickness of the oxide, and the electric constant is different from the silicon. And we know that this law holds at the junction, at the boundary. We can then write the electric field in the oxide is proportional to electric field in the silicon multiplied by the ratio between the silicon dielectric constant and the oxide dielectric constant. That is more or less 12 divided by 4, that is more or less 3. This Gauss law tells us that the field in the oxide is 3 times the field in the silicon. This means that we can evaluate the voltage drop across the thioxide thickness considering an equivalent silicon layer whose thickness is 3 times the thickness of the oxide. This is the voltage drop on the silicon. But what we are interested in is not only the voltage induced here, but we want to understand which is the behavior here at the end of the field plate, where the junction will curve again, because we don't want this curvature to be very high. For a negative bias of the field plate, we can imagine that the electric field at the end of the plate correspond to the case of a diffused silicon P+ layer with an equivalent thickness that is 3 times the thickness of the oxide. And hence, with the curvature radius that is Rj is equal to 3 multiplied by the thickness of the oxide. And with the voltage bias that is the reverse bias minus the voltage drop on the oxide. If the oxide is very thin, the voltage that we will induce on the silicon surface is very close to the reverse voltage. Delta V will be small. And the field that we induce at the end of the field plate will be very strong, since 3 times the thickness of the oxide is a small value. This simply means that we will induce a premature breakdown at the end of the field plate. On the other hand, if we use a thick oxide, the curvature at the end of the field plate will be very small, but the voltage drop under the plate on the oxide will be large. And this means that the voltage at the silicon surface will be very small, much less than the voltage on the main junction. And this means that the field plate is not effective also in this case, because we will have a breakdown near the main junction. Exactly like the field ring, also in this case, the optimum is not, the field plate will not work always in one direction, but there will be an optimum thickness of the silicon that will prevent or will maximize the improvement in the breakdown voltage. We can examine these 2 possible extreme cases. In the first case, the junction, the curvature of the main junction is 10 micron. The thickness of the depletion region, WB, at breakdown is 100 micron. And the thickness of the oxide is just 1 micron. We can then say that the radius of the curvature here is more or less 3 times the thickness of the oxide, that is 3 microns. Second case, the main junction is the same, but the thickness of the oxide is 10 micron, and the curvature of the junction, the equivalent junction here is 30 microns. Assuming a reverse bias of 1000 volts, we obtain, for the first case, the critical electric field for silicon is 20 volt per micron. The electric field through the silicon dioxide is 3 times, is 60 volts per micron. And the voltage drop on the silicon dioxide is 60 volts. It's just 1 micron thick. This means that the field plate induces here 940 volts. That is a very high voltage, very close to 1000. On the other hand, the curvature here is 10 microns, and the curvature here is just 3 microns. This means that here we get the breakdown here. In the other condition, again, the values of the critical electric field are the same, but this time the voltage drop on the silicon dioxide is 600 volts because it is 10 microns thick. And the voltage induced on the field plate, on the silicon, from the field plate is just 400 volts, quite small. We will have 30 microns of curvature, that is larger than Rj. This means that here we have smaller voltage, larger curvature. The breakdown will happen much later, much farther. The weak point here is this junction here. The breakdown will develop at the lateral side of the main junction. The optimum value is between these two values. Maybe 5 microns of thickness of silicon oxide will optimize the breakdown voltage. This is another possible solution. It must be said that a lot of effort has been posed in optimizing these field ring and field plates in order to improve the breakdown voltage. This is a possible solution. As we can see here, we have this believed? No. Okay. Is believed, the pronunciation is not correct, possibly. However, we have this kind of, this shape of silicon dioxide. This will reduce the induced voltage on the silicon surface as we move far from the junction. This is very good, but the manufacture of this one is impossible, or almost impossible. Maybe this technique is better. We have different steps with reduced voltage, but also this is not simple to manufacture. The reality is that we use a combination of floating rings and field plate to optimize the breakdown voltage. And joining these techniques with good numerical simulations, you can get a breakdown voltage that is 90% or 95% the value of the plane breakdown voltage of the plane junction.